Next, we'll give some classifications of measurable sets. And there we go, section 2.4, outer and inner approximation of Lebesgue measurable sets. So the plan is to give conditions that are equivalent to a subset of the real numbers, set E, to being measurable. And we're going to approximate, quote unquote, these measurable sets with some familiar sets, some F sigma, and some G delta sets. We've already done something similar, but slightly different from this inner and outer approximation stuff and some things we did in the past. More of that shortly. The excision property, Lemma 2.4.a, says if A is measurable and of finite measure, and A is a subset of B, then the outer measure of B set minus A is the outer measure of B minus the outer measure of A. Unsurprising, expected. Yeah, when we deal with measurable sets, then I expect nice things to happen, reasonable things to happen. Right? This looks like some sort of additivity type thing. The condition on measurability of, outer measure of A being finite avoids us running across maybe an infinity minus infinity nonsensical symbols. So that's the reason that we've got the restriction to A being finite. The excision principle looks reasonable. Here's the proof. Okay, A is measurable. So if we treat B as some subset of the real numbers and apply the definition of measurable, the Carathéodory splitting condition, then we get the outer measure of B equals the outer measure of B intersect A plus the outer measure of B intersect A complement. Carathéodory splitting condition. B is playing the role of set A we usually had in the statement of the Carathéodory splitting condition. But this is the Carathéodory splitting condition applied to measurable set A, where B is an arbitrary subset of the reals. Okay, so by the measurability of A, we get that. Amusing observation. We didn't assume the measurability of B in this process. B intersect A complement, that's equivalent to B set minus A. By the way, take that as a definition of B set minus if you like. So we've got then the outer measure of A plus the outer measure of B set minus A. Based on the observation, so we've replaced the B intersect A with A itself. A is a subset of B, so B intersect A is A itself. Since the outer measure of A is finite, we can just subtract that from both sides and get the claim. So easy enough, follows from really just a definition of measurable and this caveat disclaimer that A has to have finite outer measure to avoid a nonsensical equation. So reasonable behavior, only conditions are A is measurable and a finite outer measure. Back to the notes. We argued, stated in the notes, that exercise 2.7, problem 2.7, has one show that for any bounded set E, there's a G delta set, G containing E, with the same outer measure as E. We also, maybe in some of the supplemental stuff, mentioned something about F sigma sets that are subsets. So if we had to use inner measure to get a parallel result in terms of subsets. But we did state that for any bounded set E, we can find such a G delta set. G delta set was what? Countable intersection of open sets. And we'll see where this G delta set comes from. And we get the following result, which does mention inner and outer approximations is what we'll call these, but it does mention covering set E with a G delta set G and sort of packing inside of set E an F sigma set capital F, and getting something or other to have measure 0, outer measure 0. All right, so the statement is let E be measurable, let E be a subset of the reals, then the following conditions are equivalent to E being measurable. So E measurable implies each of these implies E measurable, each of these implies each other as well. So the claims are, for every epsilon greater than 0, there's an open set O containing E for which the outer measure of O set minus E is less than epsilon. Secondly, there's a G delta set G containing E for which the outer measure of G set minus E equals 0. And then sort of similar results for closed sets and F sigma sets, but subsets now. For each epsilon greater than 0, there's a closed set contained in E. So F is a subset of E, for which the outer measure of E set minus F is less than epsilon. So similar to what we had up here. Real difference is up here things are open and they covered E. Down here things are closed and they're subsets of E. And similar to part 2, there is an F sigma set contained in E for which the outer measure of E set minus F equals 0. Now that's different from what we said in problem 2.7. We took any bounded set and found a G delta set that covered it, that had the same outer measure as set E has. We're not talking about outer measures of sets E and G, for example, in this part 2. We're talking about the outer measure of the difference, which is something else. Up here in problem 2.7, we took any bounded set. It didn't have to be measurable up there to find a set G that satisfies this type of condition. Down here, things are different. Down here, we're, say, assuming the set is measurable and drawing a conclusion of this form, or making an assumption of this form and drawing a conclusion of measurability. The claims are equivalent, is what's being said. So this covering with a G delta set idea and looking at the outer measure of the set difference is a little bit different from what we have up here. Here we're covering E with a G delta set G, and the two sets E and G have the same outer measure. That doesn't necessarily imply that the outer measure of the difference equals 0 up here. That requires measurability. And up here, you're picking a set, you're making it bounded. So that may not apply to this particular result. We may not get the outer measure of the difference to be 0 up here. Yeah, because you're dealing with non-measurable sets. In fact, this condition implies measurability of set E. So let's go through a proof of that. Okay, this one's stretched out over a few slides. We're going to prove the first two parts are equivalent to measurability. We'll show measurability implies part 1 implies part 2, and part 2 implies measurability, showing that 1 and 2 are equivalent to measurable, the measurability of E. And then we'll make a little comment about how you deal with the closed subsets versus the open supersets, and the F sigma subsets versus the G delta supersets. Okay, so first we're going to show that if E is measurable, then property 1 happens. Okay, property 1 is where we cover set E with an open set O, called an outer approximation, ultimately, and we show the set difference is small. Part 2, we cover set E with a G delta set and show the set difference is 0. All right, so suppose E is measurable, let epsilon be greater than 0. We're going to bust this into a couple of cases. First, suppose E has finite measure. We'll take care of E having infinite measure here in a second. Okay, if E has finite measure, then from the definition of outer measure, there's an open cover of intervals, I sub k, countable collection of intervals, such that these intervals cover set E and the sums of their lengths is less than the outer measure of E plus epsilon. The fact that the outer measure of E is defined as an nth of all sums of this sort, all real numbers that result from a sum of this sort, And if we add a little bit to that inf, we get an element of the set using theorem 0.3 part B on this. The epsilon property of soups and imps is what that theorem was about. So give me a little wiggle room. I can find elements of the set. I can find, therefore, collections of bounded open intervals that cover set E, the sums of whose lengths is as given. All right. Define O to be the union of all of these intervals. Arbitrary union of open sets is open. This is a countable union. It's a countable union of open intervals. So anyhow, that's what set O is. Then certainly O is open, and E is a subset of O. E is a subset of the union of these intervals, and that's what we said what we meant when we said cover set E with intervals. Okay, let's look at the outer measure of O. Well, O is covered by these intervals as well. And that looks weird because O is made up of these intervals, but they give a covering of the open set O. Now, where we are right now, nobody said anything about those I sub k intervals being disjoint. We didn't get here like that. Here, we've got O written as a union of these intervals. For all I know, these intervals may intersect each other. The outer measure of O is the inf of the sum of the lengths of coverings. This is a particular covering. So we get the inequality. The inf is less than or equal to a particular element of the set. All righty, and to have an intuitive feel for it, yeah, remember these I sub k's, maybe they're not disjoint. So there's some overlapping going on. If they are disjoint, I would expect to get an equality. I would get an equality if they were disjoint, but we didn't get here like that. All right, now the sums of the lengths of the intervals, these were chosen in such a way that the sums of their lengths is less than the outer measure of E plus epsilon. So that gives us that inequality there. This can be rearranged. Subtract the outer measure of E from both sides to give the outer measure of O minus the outer measure of E is less than epsilon. We good with that? Yeah, that's why we needed to make the constraint that the outer measure of E was finite. If O is infinite measure, E is infinite measure, we got some nonsense here. So that's why we're applying to the particular case of E is bounded in measure, in outer measure. Not that it's a bounded set, but it's measure, its outer measure is bounded. Okay, now using the fact that E is measurable, that's what we're hypothesizing in this case. We know the outer measure of O equals the outer measure of O intersect E plus the outer measure of O intersect E complement. Yeah, that's the Carotheodori splitting condition applied to E. Here's E and E complement, where the arbitrary set of real numbers that could go here, we've chosen to be that open set O. All right. Now, O contains set E. He's a subset of O. So when we take O intersect E, that's just going to give us set E. O intersect E complement, we could write that as a set difference. Let's do that because we're headed somewhere where I want to talk about a set difference. So let's take O intersect E complement, write that as a set difference. We'll replace this with E itself because that's what it is, giving us this. The outer measure of O is the outer measure of E plus the outer measure of the set difference. Again, since we're considering the little subcase, outer measure of E is finite, then we can subtract the outer measure of E from both sides. We get the outer measure of O set minus E is the outer measure of O minus the outer measure of E. Well, now we had upstairs the outer measure of O minus the outer measure of E less than epsilon. So we draw the conclusion that the outer measure of O set minus E is less than epsilon. And that was what property 1 was. We get the outer measure of O set minus E to be less than epsilon. You give me epsilon greater than 0, I go through a process of covering E with some particular kinds of open intervals and creating an open set O, and out pops this inequality. So if E is measurable and the outer measure of E is finite, then the outer measure of O set minus E is less than epsilon. That was what claim 1 was. So now we need to do the same thing, but in the case that the outer measure of E is infinite. All right, what we're going to do is take E now and cut it into a countable number of little finite measure sets, and then apply this previous result to each of those. So take E, write it as a countable disjoint union of little e sub k's, where each of the e sub k's are measurable and of finite measure. One way to do that is given here. We could take set E and intersect it with k minus 1 to k, and let k range over all of the integers. I've broken it up to where we've intersected with k, a natural number here. So we're dealing with intervals from 0 to 1, 1 to 2, and so forth here. Here we're dealing with, say, 0 to -1, right? -1 to 0. But we're dealing with the negatives over here and the positives over here. Anyhow, we've taken the whole real line and partitioned it into these disjoint little half open, half closed intervals. Intersect those with set E, and that'll produce you a countable disjoint, because of the way the intervals are chosen, countable disjoint union of finite measure sets. Hey, E is measurable. All intervals are measurable, so these E sub k's themselves are measurable. We're in an algebra, and those are properties of that algebra, or in a sigma algebra, but those are algebra properties, just taking intersection 2 here. So each of the E sub k's are measurable. They're disjoint by construction. All right, well now we've then got each E sub k is a measurable set of finite measure. By monotonicity, its measure is at most 1. So that's pretty finite. So by what we just argued, then we know there's an open set containing E sub k, for which the outer measure of that open set, set minus E sub k, is less than epsilon over 2 to the k. That's what we just did, except for each k, we're choosing a particular open set, O sub k, covering E sub k, and we're making the measure, outer measure of the set difference small. I choose small to be epsilon over 2 to the k. That's a positive number, ain't it? You give me a positive number, then we can find such an O sub k by the first part. Of course, we've done a epsilon over 2 to the k power, because we're going to be summing some stuff here shortly to get an epsilon itself. And define O then to be the union of all of those O sub k's. All right, each O sub k covered each E sub k. Set E itself, that's what the question's about, is the union of those E sub k's. So the union of the O sub k's, set O, covers the big set E. So we've got E covered by an open set O. O set minus E would be, because we define O to be the union of the O sub k's, would be the union of the O sub k's, set minus E. That's a subset of the union of the O sub k's, set minus E sub k. Over here, we're subtracting set E. Over here, we're subtracting E sub k, a small piece of E, so we get the subset inclusion in that direction, being a little liberal with some of the set theoretic arguments, but that's a correct inequality, correct subset inclusion. So subset inclusion, I can throw maybe monotonicity at that. We've got the outer measure of O set minus E would be less than or equal to the sums of these outer measures. That's subset inclusion, so we can get that from monotonicity, say. We know the outer measure of O sub k set minus E sub k is less than epsilon over 2 to the k. That's how the O sub k's were picked. So this sum from 1 to infinity is less than this sum by that strict inequality there. Oh, and this works out just fine. We've got epsilon over 2 to the k. Bring the epsilon outside the sum. You've got a geometric series, powers of a half, that sums to 1. And so we get epsilon out. And outer measure of open set minus E less than epsilon, that was property 1. So now we've establish property 1 in the event that E is an infinite measure set, a measurable infinite measure set. Okay, so we've shown that if E is measurable, then property 1 holds. Next, I'm going to show property 1 implies property 2. Probably worth our time to look back at property 1 and property 2. Property 1 dealt with covering E with an open set. Property 2 dealt with covering E with a G delta set. Excuse me, let me run back to the statement. Property 1 said for all epsilon greater than 0, we can find an open set satisfying this condition we just established. Property 2, no epsilons, no open sets directly either, a G delta set. There's a G delta set G containing E for which this outer measure equals 0. So cover it with open sets, set difference can be made small. Cover it with an appropriate G delta set G, outer measure of that difference can be made 0. So we want to show first implies second, which shouldn't be a huge surprise. Up here we got open sets. Down here we've got a countable intersection of open sets. Up here we've got an epsilon. Down here we've replaced it with a 0. Yeah, we did some sort of limit thing, it sounds like, in passing from the open set to the G delta sets. So let's go through the proof, back to the page. Suppose 1 holds. So E can be covered with a open set such that the set difference can be made as small as you like. All right, for K a natural number, so here comes the countable part, there's an open set, O sub K, containing set E, such that the outer measure of O sub K minus E can be made less than, you tell me, epsilon. All right, telling you 1 over K. So we'll take epsilon equals 1 over K and find an open set O sub K satisfying this. Can be done for every natural number K. That's what part 1 gives you. Define G to be the intersection of all those O sub Ks. All right, the O sub Ks are open. This is a countable intersection of the O sub Ks. Then that set G is a G delta set. Since each O sub K, there it is, contains E, then the intersections of all the O sub Ks also contains E. E's a subset of each O sub K. It's a subset of the intersection of all of them. G set minus E is a subset of O sub K set minus E because G is a subset of each O sub K. G was defined to be the intersection of all of the O sub Ks. So any particular O sub K is a superset of G. So G is a subset of O sub K. So we get this set inclusion when we do the set subtraction of set E, because O sub K has more stuff in it than G has. And we've, I don't know, subtracted the same amount from both sides if you informally like. But that's a subset inclusion to which we can apply monotonicity of outer measure and say the outer measure of this is less than or equal to the outer measure of that. Outer measure of G set minus E is less than or equal to the outer measure of O sub K set minus E. And we already had that less than 1 over K upstairs. This can be done for any K a natural number. The only way you can have this number, just a number, it's the outer measure of some set. The only way you can have this number less than 1 over K and this whole for all K a natural number is for this number to be 0. Of course, all these measures are bounded below by 0, so there's no negatives that come in. And so we conclude that the outer measure of G set minus E equals 0, where G is a G delta set. That was part 2. All right, now we want to show this G delta set property implies measurable. So we've got measurable implies property 1. Now we just showed property 1 implies property 2. So we're going to link property 2 back to measurable in a third step, and that will tie together those 3 ideas. Property 1, property 2, and measurable are equivalent to each other. So suppose property 2 holds, we want to show E is measurable. All right, how are you going to show E is measurable? First guess, Kerr-Theodore splitting condition. That'd be a reasonable thing. We're going to go a different route, but that would be a reasonable thing to try. We're going to use properties of the fact that the measurable sets form a sigma algebra. It's easier than the Kerr-Theodore splitting condition. So suppose equation 2 holds, property 2, this little thing here holds, then the outer measure of G set minus E equals 0 for some G delta set G. Now, we know G set minus E is measurable. Hey, G delta sets are measurable. All Borel sets are measurable. E is measurable, so its complement is measurable. So G set minus E, or if you like, G intersect E complement is measurable, taking advantage of the sigma algebra properties of the measurable sets. So G set minus E is measurable, so its complement is measurable. G is a G delta set, so yeah, G is measurable also. And we can write set E as G intersect G set minus E complement. Let's not get bogged down in the details on that. It's a true set identity. It's not surprising. A few details wouldn't hurt, but we've got other things to do. So we can write E like this. Hey, and we know G is measurable. It's a G delta set. All G delta sets are measurable because they're Borel sets, and all Borel sets are measurable. So that's measurable. We just observed that G set minus E complement is measurable, so that's a measurable set. Intersection of two measurable sets is measurable. So set E is measurable, and that's what we were trying to show. Set E is in the sigma algebra of Lebesgue measurable sets. That is, it's measurable. So this shows us that E is measurable. Condition 1, condition 2, these are all equivalent conditions. Part 3 and part 4 deal with F sigma sets, well, with closed sets first and then F sigma sets. Hey, guess what? De Morgan can come riding to the rescue. This was left really as an exercise. De Morgan tells you how unions and intersections interact with complements. We used open sets in part 2. In part 3, we used closed sets. Well, the complement of an open set is a closed set. In part 2, we talked about G delta sets, and in part 4, we talk about F sigma set. Well, the complement of an F sigma set is a G delta set, and vice versa. So De Morgan and a little bit of bookkeeping will show part 3 and part 4 are equivalent to measurable and equivalent to all the other stuff. Just De Morgan and use the knowledge you have from the previous parts. So that gives us conditions equivalent to measurability. And this is pretty wild. The set difference here is has outer measure 0. This is telling you that measurable sets in this sense are a lot like G delta sets. They're a lot like F sigma sets as well in this sense. Every measurable set differs from a G delta superset by a set of measure 0. Every measurable set differs from an F sigma subset by a set of measure 0. So that might be an alternative way to say that. Turns out sets of measure 0 can be pretty complicated things themselves. It's a little, 0 is bigger than you might have thought initially. That's one thing you learned from this class. I can do a lot of weird stuff with a measure 0 set. The G delta and the F sigma presented above are called the outer approximation and the inner approximation. These approximate measurable sets in the sense described in that theorem. F and G, the F sigma set and the G delta set are Borel. All F sigma sets are Borel. All G delta sets are Borel. All F sigma delta sets are Borel sets. That was just a collection of Borel sets. We had a chance at describing what they look like. But these are certainly Borel sets. Borel sets are measurable. We made a note of that after proposition 2.8. So we can apply some additivity when we're dealing with measurable sets. Proposition 213. Not stated in Royden and Fitzpatrick yet, but we proved it in the previous section because we could. We had the equipment. That was the time to do it, in my opinion. But if we take the outer measure of E disjoint union G set minus E, so here's set E, here's that little sliver of set that includes things in G but not in E. G is a superset of E. These are disjoint, of course, so countable additivity, finite additivity, tells us that the measure of the disjoint union is a sum of the measures, outer measure. Technically, we haven't defined measure yet, but Lebesgue measure is outer measure, just restricted to measurable sets. So it does definitely matter that E is measurable and G set minus E is also measurable. I don't have measurable sets. I can't draw this very reasonable conclusion. That's why measurable sets are so desirable. This is the outer measure of E plus the outer measure of G set minus E. Well, that's the same as the outer measure of G because this is set G over here. So the conclusion we can draw, since this has measure 0, is that the outer measure of E equals the outer measure of G. We can similarly show the outer measure of E equals the outer measure of that F sigma subset F. Same argument. We can conclude, the words here are chosen, they sound informal, but they're actually chosen with great care. We're going to define almost before this is over with, before this measure theory is over with. We'll define what almost means. So the following highlighted statement is our conclusion from all of this. Every measurable set is almost an F sigma set and almost a G delta set. Almost in the sense explained in Theorem 211, the second and the fourth parts that dealt with the F sigma and G delta sets. To be a bit more precise, every measurable set differs from an F sigma subset by a set of measure 0 and differs from a G delta superset by a set of measure 0. So it matters where those sets were. In the study of inner and outer measure, if we've looked into the outer measure stuff, there's a supplement that goes into some detail. We mentioned it in passing when we developed measure. The inner measure part we dealt with in passing. Outer measure part we dealt with in great depth. But there's a supplement that talks more about inner measure. We introduced the measurable cover and the measurable kernel, as mentioned before. I guess it's a previous section, I think. We took an arbitrary set, covered it with a G delta set, covered it with an F sigma, or packed inside of it an F sigma set. And we saw that the outer measure of E and the outer measure of G were the same. Not making an assumption that E is measurable this time. We saw in the supplement that the inner measure of E equals the inner measure of F. So these two are of the same inner measure. These two are of the same outer measure. Now that doesn't mean F and G have the same measures. It will if E is measurable, but it doesn't otherwise. So when we did that measurable cover, measurable kernel stuff back when, we weren't necessarily dealing with a measurable set E. And things didn't fit together as tightly because we didn't have a measurable set. You got a nice measurable set, you're good to go. You can get these F sigma and G delta sets really to have the same measure. So we weren't talking about measurable sets in that conversation about measurable covers and measurable kernels. This inner approximation and outer approximation stuff, it looks like what we did with that other stuff. But it's not, because here we've assumed we've got measurable sets. So inner approximation, inner and outer approximation are properties of measurable sets. Measurable kernel and measurable cover, that's associated with any set of real numbers. We want to stay away from all sets of real numbers because weird stuff happens with their measures. We'll restrict our attentions largely to measurable sets. Okay, one final result coming up. First, we're going to define a thing called a symmetric difference of sets. A and B is done with an eye towards sets of real numbers, but stated in terms of any old sets A and B. The symmetric difference A, symmetric difference B, is defined to be A set minus B union B set minus A. It's a disjoint union, in fact. It's the stuff in A that's not in B, union with the stuff in B that's not in A. You can easily draw a Venn diagram of that. Turns out we can relate symmetric differences to measures being small as well when dealing with measurable sets. If A and B are measurable sets of real numbers, then so are the set differences because we're in an algebra. And by countable additivity, we could write the outer measure of A symmetric difference with B as the sum of the outer measures of the constituent parts. Those are disjoint. This is the stuff in A that's not in B. This is stuff in B that's not in A. So certainly these are disjoint sets, by the way. So countable additivity, it's overkill, finite additivity, tells us you can measure symmetric differences by taking sums of those two little outer measures. Suppose, Theorem 212, E is measurable and a finite outer measure. Then for every epsilon greater than 0, there is, here's the surprise word, a finite disjoint collection of open intervals I sub k, k equals 1 to n this time, for which, if we define O to be the union of those intervals, those finite number of intervals, then the outer measure of the set symmetric difference of measurable set E and set O, that is the outer measure of E set minus O plus the outer measure of O set minus E, that can be made small. Let's go ahead and read this comment before we do this last little proof. The textbook states that this result shows that finite measurable sets are nearly a finite disjoint union of intervals. We're going to use the word almost in a very precise way. We're going to use the word nearly in a consistent but informal way. In general, when we can approximate a set, later a function, in chapter, I think it's chapter 4, we'll talk about measurable functions. When we can approximate something to within an arbitrary amount epsilon, and that will deal with measures of sets, we'll use the word nearly. So we're getting this to be within epsilon of 0. So we'd say something about nearly. This set is nearly a finite union of open intervals. Set E differs in a symmetric difference way from an open set that's a finite union of open intervals by an amount epsilon. That's the sense in which they use nearly. The big word again is finite collection of intervals in Theorem 212. And they gave me an epsilon amount. I can do a bunch of damage with a set of measure 0. You give me an epsilon amount of room to wiggle around in with this measure stuff, and I can do a bunch of stuff. The fact that we're able to talk finite union of open intervals reflects that idea. Okay, so let's look at the proof of this. I think it's only a couple slides. So claim is finite collection of intervals. All right, so start with a given epsilon greater than 0. Since E's measurable, then this thing we just did, part 1, where we covered a set with an open set, a measurable set we covered with an open set, G, we called it before. We know there exists an open set, we're going to call it U this time for fun. Open set U, such that E is a subset of U, so open set containing E, and the outer measure of the difference is less than epsilon over 2. We were given by hypothesis that E has finite measure, so we can use the excision principle, which allows us to take the outer measure of U set minus E and write it as the difference of the measures. Provided this was a set of finite measure, the excision property, the first thing we did in this section, allowed us to take outer measures of set differences as differences of outer measures. Now I can move this to the other side and write this as outer measure of U equals the outer measure of E plus the measure here. of the difference. We know this to be less than epsilon over 2. That's what the previous theorem gives us. So we've got an outer measure of E plus epsilon over 2 on the right-hand side. We need the fact that the outer measure of U is finite for some reasons to be made apparent on the next slide. Here we've got the outer measure of U is less than outer measure of E plus epsilon over 2. Outer measure of E, well, it's finite. You add epsilon over 2 to it, you've still got something finite. So indeed, the outer measure of U is finite. I know what U is. It's an open set. Hey, I know what open sets of real numbers look like. They are, theorem 0.7, I guess is where we prove this, countable disjoint unions of open intervals. Set U being an open set, let's change this conversation to open intervals. We got to make it a conversation about open intervals at some point. So write U as a disjoint union, countable disjoint union, too many for our purposes in this theorem, but countable disjoint union of open intervals I sub k. Each interval is measurable. We showed all intervals are measurable. Outer measure of an interval is its length. U is measurable. The I sub k's are measurable. So what we're going to do is take a measure, outer measure of U, and an outer measure of this set over here. We know that the outer measure of the union is less than or equal to the outer measure. Oops, what have we done here? Excuse me. Countable union. Okay, next. Okay, finite additivity and monotonicity. Okay, so I wonder where this inequality came from, monotonicity. All right, so if we sum from 1 to n, any n for the sake of illustration, if we sum from 1 to n the lengths of those intervals, that's the measure of the union. That's the finite additivity part. There's proposition 2.6. The union of a finite number of the I sub k's, well, that's a subset of set U. It's the union of all infinite of those I sub k's. So this is a subset of U, and monotonicity gives us that inequality. We just showed that the outer measure of U is finite. So here's what we've got. For any natural number n, when you add up the lengths of the first n of those intervals, I sub k, you get something finite. It's bounded above by this fixed finite number, the outer measure of U. So when you add up, take a limit as n approaches infinity, when you add up all of these things, it must be finite. In fact, it's bounded above by the outer measure of U. That's why we showed the outer measure of U was finite in hindsight. So we've got a sum here of non-negative real numbers, series, excuse me. We got a series of non-negative real numbers which converges. Okay, that's a summable sequence then of real numbers. And so the only time you get a series to converge is when the tail of the series is small, a property from calculus 2 about summability of series. So if we could add up the first bunch of these things, and what's left can be made small, a property of summable series, summable positive term series. So there's an n, natural number, such that if we sum from n plus 1 to infinity, that tail, that's what I mean by the tail, the infinite tail of that series, can be made small. Let's make it less than epsilon over 2. All right, so depending on your knowledge of summable positive term series is how it's stated in the calculus book, the tail must be small. You probably saw this in senior level analysis as well. So here's what we've got. We'll define O to be, this is why we used the letter U before, we'll define O to be the finite union of these n I sub k, where the n is determined from this equation, this condition. O set minus E is a subset of U set minus E because O is a subset of U. O is the union of the first n of those intervals. U is a union of all of them. So O is a subset of U. So we get this relationship here. Trying to get this conclusion. Okay, so monotonicity and this fact, so we established this above, outer measure of U set minus E was less than epsilon over 2. Here's the other epsilon over 2 we're going to use, but paste them together. But this was established above. We've got that the outer measure of O set minus E is less than or equal to the outer measure of U set minus E. The subset thing, that's monotonicity, that inequality. And the outer measure of U set minus E is less than epsilon over 2. We did that somewhere on a previous slide. So we've got the outer measure of O set minus E less than epsilon over 2. We're trying to show the outer measure of O set minus E plus the outer measure of E set minus O. So we still got that part to do. So we'll get another epsilon over 2 from that. On the other hand, E is a subset of U. So E set minus O is a subset of U set minus O, where set minus O is the union of the first n. U is the union of all of those intervals. So when I do the set subtraction, you're just left with a tail, and you know the tail is going to be small. So E set minus O, E is a subset of U, so this set is a subset of that set. I can explicitly write this in terms of the tails of those intervals, union of the n plus 1 to infinity of the I sub k intervals. So we have E set minus O covered with a bunch of open intervals. The sums of the lengths of those intervals we know to be less than epsilon over 2. That's where the n came from. Sum of the intervals being an open cover of E set minus O with bounded open intervals, and this being an infimum. So I say by the definition of outer measure, this is a particular open cover. Particular open covers are greater than or equal to the infima, the outer measures themselves. This is less than epsilon over 2, so the outer measure of E set minus O is less than epsilon over 2, and there you go. Outer measure of O set minus E, less than epsilon over 2, plus the outer measure of E set minus O, less than epsilon over 2. That sum is less than epsilon over 2 plus epsilon over 2 equals epsilon, and there's that result. So we're doing an approximation of a finite outer measure measurable set with an open set. And we can make that open set as close as you'd like, except for within 0, in a symmetric difference sense. The outer measure of the symmetric difference can be as small as you like. And we did it with an open set that consisted only of a finite union of open intervals. And we saw ultimately we chose them such that they were disjoint. And that's what we'll mean by nearly later on. But there's just some properties of measurable sets. This we'll use somewhat. For now, it'll see a little more light of day. I think maybe in chapter 5. I think it is. It will use this a little bit more. But we've got this inner and outer approximation. These are some properties of measurable sets. We haven't formally, well, you and I have in the videos, but the book hasn't formally defined Lebesgue measure yet. So that's coming soon. We'll define Lebesgue measure. The book will establish, I think it's in section 2.5, that Lebesgue measure is countably additive. Well, we've already really done that. I think it was proposition 2.13. I even remembered it was such a big deal. So next section, we'll formally define Lebesgue measure and look at some more properties. Section after that, we'll look into the fact that not all sets are measurable by showing the existence in a very exotic way of a non-measurable set. So have a nice day. I will see you in section 2.5, which is up next. Bye-bye.